Hi everyone, I'm Irene Japan, your MC for this session. We have all seen LLMs do incredible things, but what does it really mean when we say they can reason? Is it magic or is there a method behind the mystery? To guide us through this fascinating frontier, we have Irene lead data scientist at Agile Lab with a rich background in both academic research and industry leadership. She has a gift for making complex ideas clear. So join me in welcoming Irene Donato as she presents from chain of thought to agentic AI, demystifying reasoning in LLMs.
Hi everyone, I'm going to speak about reasoning in large language model and what does it mean for a large language model to reason. But before I start, a small introduction about me. I'm a senior data scientist at Agile Lab, and at the moment I also coordinate the data science and AI practice. Agile Lab is a small tech company, well, not very small, there are 200 of us, and it is focused on data engineer, AI solution and data platform. Before we speak about reasoning model, we need to understand what large language models are. They are a machine learning model based on a particular kind of neural network called transformer. And they are trained to predict the next word or token. Let's think word just to make things simple. So, for example, if we input a large language model with a sentence like sudo make me a, it will output sandwich. This is because this is a famous meme in the tech company, and as the large language model are trained on a huge amount of data found on the web, so maybe almost all the data you can find on the web, they have seen this meme many times. And so they will output this sentence. So you can think of large language model as parrot that mimic human languages. Okay, now I try to input this sentence on ChatGPT 5 and it doesn't output sandwich. And why this? Well, this is due to the fact that after the pre-training, the model undergoes a post-training process. So in total we have 4 stages. First stage where all the text that then will be used to train the model are divided into small pieces, the tokens. Second stage where we train the model to predict the next word using all the text that we can find on the web and that are considered safety enough and curated enough. In the third stage, we continue this training process, but with human expert curated answer. And lastly, there is a reinforcement learning stage where the model learns to generate more preferable answer. This is done in different ways nowadays. Originally, it was done asking to human expert to rank the answers. Interestingly, by slightly changing this post-training process, we can obtain specialized large language models. And exactly in the last year, we have seen the rise of many different specializations for large language models, such as web search large language models, domain-specific large language models, multimodal large language models, and so on. And one of these specializations is exactly the reasoning models. But is a large language model able to reason? Well, to answer this question, we first need to define what reasoning means for a large language model, and there is not a complete agreement on this. So some people think that whenever a large language model solve a problem that humans will solve via reasoning, we can call that reasoning. But others give a more specific definition, and they say that reasoning for a large language model is the process of generating intermediate step tokens between input and output that help reach the final answer. And we are going to adopt this second definition along this talk. So we can see an example. If we ask to a model, if you save $25 per week, how many much will you have saved after 1 week? If the model answer just how much you will save, this is not reasoning. Whereas if the model generate tokens like a year has 22 weeks, so and so on, this can be considered the reason of the model. And this is not a new idea. Already in 2017, DeepMind introduced natural language to solve math problem, and they trained a model from scratch using question and explanation of the answer and answers. At the time, transformers were not being invented yet, so they have used long short-term memory models. But anyway, they saw that adding explanation to the answer highly increase the math, the ability of the model to solve math problem. And then this has also been used for fine-tuning the model, this idea. So for example, in 2007 and in 2021 has been released GSM8K, that is a dataset that nowadays also uses a benchmark to test the model in their mathematical ability. And 8K stands for 8,000 examples. So in fact this dataset contains 8,000 math problem with the explanation, and this has been used to train GPT models, and have shown that fine-tuning with this explanation again increase the math ability of the model. Supervised fine-tuning is what has inspired chain-of-thought prompting, a well-known technique to encourage the model to output more token before the final answer. So let's see with an example what we mean with this technique and how we can apply this technique. So on the right we can see that we have the same input given to a model with a small difference. In one we give question, answer, and then again question. In the second one we give question, answer with the addition of an explanation highlighted in blue, and again the question. And we see that when we add the explanation, the model output contain the explanation as well, and this helps the model to arrive to the right answer, 9, whereas without explanation the answer was wrong. And so this technique applied to Palm has bring this model from 80% of accuracy with just standard prompt to 57% of accuracy. We can have two variants of chain-of-thought prompting. The first one, few-shot chain-of-thought prompting, is the one we have just seen, but then we can also use zero-shot chain-of-thought prompting, where we just add a sentence like let's think step by step. This encourages the model to output an explanation or to reason step by step. And so we can see here with an example that just adding let's think step by step make the model reach the right answer. We have seen training with intermediate steps, fine-tuning with intermediate steps, and prompting with intermediate steps. So the key insight is that what really matters are these intermediate steps. And this is what has inspired inference time scaling, a technique that increases the computational resources at inference time instead that at training time. And chain of thought prompting can be think of an inference time scaling as well. One of the most interesting technique for inference time scaling is called chain of thought decoding. So if you look at the pink box on the right, you can see how large language model work. They generate a probability over all possible token for each new token they generate. So the new token can be generated with greedy decoding, where the model just pick the token with the highest probability, or by sampling on this probability. So here we can have also a temperature. The higher the temperature, the more creative the answer. When we set the temperature to 0, we come back to greedy decoding. So this chain of thought decoding alters the decoding process. So instead of just picking the first most probable the token with the highest probability, it selects k token, let's say 5 or 7 tokens. The idea behind the chain of thought decoding is that the reasoning ability is already into the model. We just need to alter the decoding process to encourage the model to reason. So maybe the first path that the model follow is not going to reason, but in other path it can reason and it can generate better answer. So let's see it with an example. Here we have a question. I have 3 apples. My dad has 2 more apples than me. How many apples do we have in total? So the token with the highest probability is 5. Then we have I. Then we have we. Then and so on. And we let the model continue generating the answer from these 5 first token. And so we see that the first answer is wrong, is 5 apples, and is a short one. Then we have a longer answer, where we can see that there is reasoning to the answer. The answer is, I have 3 apples. My dad has 2 more apples than me, so he has 5 apples. 3 plus 5 equals 8. We have 8 apples in total, and this answer is correct, and so on. Since these models are able to reach the correct answer many times, we can use this altered decoding process to generate multiple responses and then pick the most frequent one. So, for example, on the example on the right, you see that we reach the correct answer 2 times out of 3. So, actually 4 times out of 6, so then with a probability of 2 out of 3. And interestingly, also, if we look at the probability in the token that contain the answer, we can see that this probability is higher when the answer is correct. And also has been seen that using this technique on the GSM-8K benchmark has increased the accuracy of PALM from 58% to 75%. This plot shows the relation between accuracy and consistency. When the model reasoning paths agree more, the final answers are more accurate. And so we can use this principle also to calibrate the model. So we have seen techniques that encourage the model to emit more tokens and to reason, but this strategy can be found also by the model itself, and this is what has been proved with the release of DeepSeek R1 in January of this year. The researcher trained the model without supervised fine-tuning, but just with reinforcement learning with verifiable rewards. And they have shown that the model learns by itself to increase the length of its response. So in fact in this plot you can see on the left the accuracy increasing during the training, and on the right the average length of the model answers. Then DeepSeek show also that this reasoning ability can be transferred from a large heavy model to a small model with a distillation process. To conclude, I just want to remember that even if a reasoning model reach higher accuracy, they also comes with a cost in compute and a cost in time that we expect for the final answer. So we only should select this model when we really need a reasoning ability and not for simple queries.
What an eye-opening session. Irene just showed us that LLMs reason by analyzing data, applying logic, and solving problems step by step. Irene just gave us a practical framework to decide when reasoning matters, how to use it effectively and responsibly. Remember that when you know how to structure problems for a LLM model, you unlock smarter, more consistent answers. A huge thank you to Irene for this insightful session, and thank you all for keeping the PyLadies Con 2025 energy alive.